This is the Variation in Growth lecture. Today we are going to be discussing not only growth, but we're also going to look at other quantitative measures that vary among individuals. Before we get into the growth aspect of human variation, I wanted to begin by talking briefly about some of the other quantitative traits that vary among individuals and among populations. These traits are referred to as anthropometric traits. The term anthropometric literally means human measures, but it refers to the measurements of external dimensions of the human body. These can include measurements of height and weight, measurements of the face, measurements of the skull, and various body measures like body mass index, sitting height, skin fold measures. These are measured by anthropologists to assess variation in physical size and shape of the body and the skull. And because these are quantitative traits, they are jointly influenced by genetic inheritance and environment. This also means that they can change during the life cycle, so there's a developmental component to them as well. There are a number of anthropometric measures, and I've included a list here, but for these various measures there are different instruments that are used. However, keep in mind that each one of these measures has a precise and a systematic protocol. Most of these have precise definitions and precise measuring protocols. This makes it standardized so that ideally all anthropologists are measuring individuals in the same exact way. One of the most common measures is weight. Weight is measured in kilograms and is a composite measure of body size. It includes a number of components like bone, fat, and muscle. Stature is also a very common measurement that we see in the field of anthropology. Stature is properly measured using an anthropometer. This is a long rod that has movable ends. You can see one pictured here on the slide, and height is measured typically in centimeters or millimeters. Body mass index is the combination of weight and stature, where weight is measured in kilograms and height or stature is measured in meters. BMI, or body mass index, is most often used for epidemiological studies. Typically it's used as an approximate measure for obesity and as a risk factor for many diseases. BMI is used as a rough index of relative weight. So values between 19 and 24.9 are considered normal. Values between 25 and 29.9 are considered overweight. And values equal to or greater than 30 are considered obese. This is a measure that does have issues, however. For example, someone with an athletic build would have a higher weight, but the weight is reflecting muscle mass, it's not reflecting fat. So in this case, BMI would provide an overestimate of the amount of body fat. So it's not always the best measure of variation. However, it is one that is used in a lot of epidemiological studies to study variation in weight and how that could be contributed to diets in different populations. Sitting height is a body measure that provides information on relative body length. Sitting height is measured by having the subject sit on a table, and then you measure the height from the surface of the table to the top of the head. There are two body length measures that can be estimated from this. The first is subischal length, and this is an estimate of lower body length. This is calculated by subtracting sitting height from stature. The Cormick index is a measure of relative sitting height calculated by dividing sitting height by stature and multiplying by 100. This provides a ratio. So in other words, if your Cormick index, for example, is 52%, this means that 52% of the person's height is due to their upper body length and 48% is due to their lower body length. So a Cormick index of 50% or higher is indicating that the individual has a really long torso, while a value that's less than 50% is indicating that the individual has really long legs. This measurement's been shown to be variable across populations. For example, Australian Aborigines and some Africans have Cormick indexes below 50. Asians and Native Americans have relatively long torsos, and they generally have indices, or those populations generally have indices of 50 or higher. So keep in mind that this is reflecting differences in sitting height, but it's also really a reflection of differences in climate. And we'll discuss this more later, but this is also a measurement that shows extreme variation around the mean as well. There are also various body breadth measurements. Biacromial breadth, pictured here, is a measure of body width across the shoulders. Biiliac breadth is a measure of the body width across the hips. Chest breadth and chest depth is a measure of the size of the thoracic region from side to side and front to back. Body circumferences are also taken, which include chest circumference and waist circumference. Measuring skin folds is one way to assess body composition. This is often done by measuring skin fold thickness at different parts of the body, which is a measure of subcutaneous fat. This is done by grabbing a fold of skin and measuring the double fold with a skin fold caliper, which you can see pictured here in the slide. There are 3 body sites that are measured, which include subscapular skin fold. This is located immediately below the bottom margin of the shoulder blade. There's also a triceps skin fold measurement, which is measured on the back of the arm, halfway from the shoulder to the elbow. And there's also a calf skin fold measurement, which is taken on the back of the leg. These measurements are usually used to predict body density. There are 3 commonly used head measures in the field of anthropology as well. Head length measures the overall length of the skull. Head breadth is measured as the greatest width across the back of the skull, which you can see pictured here on the slide. Head height is measured using an anthropometer and is the distance from the ear hole to the top of the head. Oftentimes, head length and breadth are used to calculate an index of cranial shape, which is referred to as the cephalic index. This is a measure that was created by Anders Retzius, which we talked about in the beginning of the semester, and it's calculated by dividing breadth by the length and multiplying by 100. This measurement was once thought to be an objective way to classify individuals into different races. And this is what we talked about in the beginning of the semester, was cephalic index being used sort of as a measurement of brain size, and kind of using that as to classify races. There is a correspondence between cephalic index and geographic origin. So it does seem to make some sense, but again, this is just clinal distribution of variation. For example, sub-Saharan Africans tend to have a narrower tend to have narrower sized heads when compared to Europeans, and Europeans generally have broad heads. While there seems to be a clinal distribution to this measurement, there is considerable variation within geographic regions where variation overlaps. And so, for example, Koreans and Germans have the same cephalic index of 83%. So there's a relationship between cephalic index and geographic location, but it doesn't correspond to discrete groups of races. Mean cephalic indexes of humans have been shown to correlate with climate, so that individuals found in colder climates, on average, will have higher cephalic index values, and individuals in warm climates have lower values. Three craniofacial breath measurements are often used in anthropometric studies. These include minimum frontal diameter, which is the width between the indentations of the skull above the eye orbits. Bizygomatic breadth is the facial width of the outermost cheeks, and bigonial breadth is the width across the rear portion of the jaw. There are also two commonly used measures of the nose height and nose breadth. Both of these measurements are taken using a sliding caliper. As I've previously mentioned, variation in these anthropometric traits is due to genetic inheritance. It's also due to environment and development. So what I want to do is talk about these in reference to what we know about variation within populations. We will start with genetic variation and then go into a discussion on human growth. Anthropometric traits differ between individuals, and this distribution reflects inheritance of different genes. There have been a number of studies conducted on the role that genetics play in producing this variation. These are primarily done through estimates of heritability and are oftentimes specific to one population. We haven't gone into too much detail on the mathematics behind calculations of heritability, but heritability is measured as a proportion. In other words, it's a measure of the proportion of total variation due to genetic variation. So it's asking, okay, here's the variation in this trait in a population. How much of this variation that we are seeing, how much of it is due to genetics? It has a numerical range of 0 to 1. So 0 would mean that the genes do not contribute to all of the phenotypic variation. Then on the other extreme, 1 means that genes are the only reason for the phenotypic variation. In general, anthropometric traits show moderate heritability, typically in a range of 0.3 to 0.6. Of course, heritability is dependent upon the specific trait that we are referring to. So, for instance, measures of body fat and mass show lower heritability than traits that are related to craniofacial measures. One example study is Dever et al., Dever and colleagues, who derived estimates of transmittability for 34 different anthropometric traits in a Mennonite population. Transmittability is simply an estimate of the parental influence on a trait. So this is essentially estimating both the genetic inheritance of the trait and aspects of the shared environment. As you would expect, parents and offspring are sharing the same type of environment. They found that body and limb proportions were most heritable, and measures of body fat and body circumference were least heritable. This makes sense because body fat is strongly influenced by lots of non-genetic factors, things like diet. It's affected by exercise. It has also been shown that as environmental variation changes, heritability changes in the opposite direction. So for example, the lower the environmental variation, the higher the heritability. So for instance, studies on stature have shown that infants have a higher heritability than adults. And this is just reflecting the fact that environmental factors hasn't really begun to affect infant body length, while adult stature reflects this lifelong non-genetic influence. Development is another factor that affects quantitative traits or anthropometric traits. This will be the main part of our lecture today, and we're going to go into more detail about human growth than we did for the genetic influences. Let's start by talking about a few basic things to know about human growth. For studies of human growth, there are two phases. Prenatal growth is growth before birth. Postnatal growth is growth after birth. We're primarily going to focus on postnatal growth. There are also two main types of studies that are conducted, and these include these studies are done for studies of human growth, and they include cross-sectional studies and longitudinal studies. A cross-sectional study is one that compares individuals at different ages, but they are all measured at the same point in time. For instance, an example of this would be to assess differences in height between girls at different ages to approximate the changes that occur during different ages as the girls grow. So what is the average height of a 6-year-old girl compared to the average height of a 7-year-old girl? This type of study is a way to assess change throughout growth, but keep in mind that it isn't actually observing the change of each individual, but it's making an inference based upon average height in various samples. This is essentially what I did for my dissertation research in assessing growth patterns that exist in different bones of the face and how they change from the age 7 to 17. Ideally, the best assessment that exists in different bones of the face, the best assessment of this would be to watch each individual as they grow from age 7 to 17, but because this is very difficult to do and requires a long-term commitment, oftentimes studies are conducted that will utilize a lot of individuals for each age group and assess what the average shape change is from one age group to the next. Another approach is a longitudinal study, and this is where comparisons of the same individuals at different points in their lives are assessed. So this means that the researcher is watching the same or tracking the same individual over as much of their postnatal growth as possible by returning to measure them year after year after year. So this is an idea representation of growth. However, they take a great deal of time, and it always poses issues in terms of keeping the original subjects in the research, because you'll have subjects that will move away or they won't want to be a part of a long-term project anymore. Another kind of introductory thing to discuss before we move on is that the process of human growth is typically analyzed or visualized using growth curves. Distance curves is one type used, which is a plot of size measured over time. So for example, you can see one pictured here on the slide. This depicts stature in centimeters for boys and girls over time. And as you can see, There's an obvious point where boys and girls increase rapidly in their stature. This also shows that growth isn't constant, but that more height is gained at particular points during an individual's lifetime. Growth curves are useful because it provides a way to easily compare between different samples or different populations. This is an example here of stature on a growth curve, but other anthropometric measures can also be put into a growth curve, but not all measurements are going to follow the same curve. For instance, head measures increase more rapidly during infancy and childhood than stature actually increases. So what influences human growth? Growth is partially affected by genetic factors. This should make sense to most of us because typically our body size as adults is on average pretty close to our parents' heights. Tall parents generally have tall children. In fact, height is a polygenic trait. So this means that it's coded for genetically by multiple genes. So you're going to receive multiple genes from mom and multiple genes from dad, and those will work together to contribute to your genetic potential for height. There's also an environmental factor that plays a role in human growth. Things like diet, disease, these can have major impacts on growth and can cause deviations from the expected pattern. Proper nutrition is critical in determining if a person reaches their genetic potential for growth. The proportion of nutrients needed for proper growth changes throughout our life. Proper nutrients is most important during infancy, childhood, and puberty. Too much nutrients can make just as much of an impact as too little. Too much nutrients during these really important life cycles can lead to an overabundance of fat, which can lead to a number of health problems. Too little nutrients, though, can delay maturation and produce a smaller adult body size. Poor nutrition slows down growth, and this unfortunately affects a great deal of the world. Not only does it delay growth, but it suppresses the immune system and increases susceptibility to disease and death. Disease also affects human growth. In undernourished populations, there's a cycle of poor nutrition and infectious disease, with the two sort of impacting one another. The onset of disease can lead to a reduction in nutritional status, which then lowers their immune system even more. So it's one of those examples that is a continuous cycle of buildup that's really difficult to overcome. But not only that, it's kind of an example of how much biology and environment and culture are kind of always interplaying with each other. Hormones can also affect growth. There are a lot of different kinds of hormones that affect growth, but one being the growth hormone. This is secreted by the pituitary gland and influences growth by affecting protein synthesis and the rate of cell multiplication. Thyroxine is a hormone produced by the thyroid gland and influences oxygen consumption by bodily tissues. And there are also sex hormones like androgens for male and estrogens for female that stimulate growth and development of secondary sex characteristics and also affect patterns of body growth differently for males and for females. Socioeconomic influences is another one of those factors that's related to others that we've discussed, since it often directly affects nutrition, the prevalence of disease, and access to health care. There's an interesting relationship between social class and growth. In many areas, upper class children on average tend to be larger and grow more quickly compared to children of lower class families. However, there's an exception to this in that lower class children have also been shown to have more prevalence of obesity. Also, in relation to socioeconomics, is that many studies have revealed that economically developed societies tend to have children that are often larger and grow more quickly. For instance, studies have shown children growing up in an urban environment grow more quickly than those that grow up in a rural environment. However, there's also some debate over whether this is actually due to economic development or due to differences in physical activity as a result of their environment. What I mean is that rural children are documented to have a lower caloric intake and have more physical activity than children in an urban environment. Another influence of social growth, though, is family size. On average, children from larger families tend to grow more slowly than those from smaller families, and this is just likely due to less nutrition availability per family member. Another pattern to be aware of in relationship to human growth is that of secular change. Secular change is defined as a change in the average pattern of human growth from generation to generation. In most economically developed populations, average height and weight have increased from one generation to the next. This reflects different changes in environments, like improvements in nutrition, or it could also reflect parts of the or times during the environment where nutrition is being depleted, and like the Great Depression era. So individuals in recent generations are more likely to reach their genetic potential. Here is an example of secular change in the height of Japanese children. This is documented from 1900 to 1971, and this graph showing the average height of 10-year-old Japanese boys. As you can see, there is a height increase from around 124 centimeters in height from 1700 to around 136 centimeters in the year 1971. So an increase of about 12 centimeters. You'll also notice a very dramatic height decrease between the years of 1940 and 1948, which is the period of time for World War II, which accounted for a period of time of nutritional deficiency in Japan. So since then, there's been a rapid increase in the nutritional status of Japanese children. This is just one example of one population, but secular change has been documented in a number of populations. Aging has also been shown to affect anthropometric measures. In particular, it affects weight and stature. For instance, weight in general increases during middle age and then declines amongst the most elderly. Stature has also been shown to decrease with aging due to bone loss and compression of intervertebral disc and flattening of the feet. Now that we've discussed anthropometric variation within populations and the various causes for variation within populations, I want to turn now to talk about variation among populations. In particular, we're going to focus on how anthropometric variation is correlated with environmental variation. environmental factors, which include climate and habitat. There are some anthropometric measures that show a correlation with specific climate variables. These include average annual temperature and humidity levels. This variation is just a reflection of the past genetic adaptation to specific climates. So while there are definite trends that can be seen, it's simply due to natural selection that has occurred in the past populations. In the 19th century, a German zoologist by the name of Carl Bergmann studied various mammalian species and noticed a trend in their body size and their environment. There was a tendency for populations to have a smaller body size and a more linear body size when they occupied a hot climate. On the other hand, populations that occupied cold climates would have bodies that were larger in size and just overall more stocky, less linear in body shape. Bergman hypothesized that body size and shape was a factor that affected heat loss. In order for ourselves and other mammalian species to maintain a constant body temperature, we have to have some way to regulate heat loss. I always like to explain this rule by applying it to an example. If you think about aluminum foil, right? I give this example in my Intro to Physical Anthropology class. If you think about a piece of aluminum foil, let's say we have two pieces of aluminum foil. I turn the oven to 350 degrees. I put one piece of aluminum foil in there that stays completely flat, and then I put another piece of aluminum foil in there that I've balled up into a really tight ball. If you were to leave those pieces in the oven for, let's say, 15 minutes, and then take them out, which one would burn you? You could pick up the one that's flat, right? Because it has more surface area kind of dispersing that heat across it, as opposed to the one that you've balled up and squished up into the oven. It's going to hold in more heat. So it's this whole idea of a volume size in terms of the relationship to the body. Another zoologist added to Bergman's observations by applying it to the size of an organism's limbs. Allen proposed that organisms that had short and stocky limbs relative to their body size would occupy cold climates, while individuals that had long and linear limbs would occupy hotter climates. So these two observations have become known together as the Bergman-Allen rules. In general, these rules apply to humans, and I say in general because there are other factors that can influence population averages. But in general, the Bergman-Allen rules apply to humans. Derek Roberts conducted a number of studies throughout the 1950s and 60s in applying the Bergman-Allen rules and found that the average weight declines with increasing temperature. He also found that there was a negative relationship between the Cormick index, and remember this is just a measure of relative sitting height. There was a relationship between the Cormick index with average annual temperature. So in other words, a low Cormick index reflects shorter legs, so that the lower limbs are shorter in colder climates and longer in hot climates. So leg length relative to stature increases with annual average temperature. There's also been research that shows that Bergman-Allen rules can be applied to the size and shape of the human head. Research by Bills from the 1970s showed that variation in overall head measurements is correlated with latitudes, so that populations that are native to cold climates portray a relatively broader and larger skull compared to populations native to warm climates. When Bergman-Allen rules are applied to this, it makes sense that broader skulls will lose less heat in colder climates. So having a broader, larger skull is actually helping to maintain a constant body temperature, while narrower skulls will lose more heat, and therefore they're better suited for warmer types of environments. There is also a correlation seen in nasal size and shape with climate. Native populations to cold environments portray a high and narrow nasal opening, while populations in warmer climates portray a short and wide nasal opening. There's also research that shows nasal size and shape is correlated with humidity levels as well. I should note here that in these studies and in all of the previous ones that we have discussed, these are studies that are primarily based upon correlations and show that there are climatic correlations with anthropometrics. In other words, just because a correlation exists, this does not imply causation. Remember, for something to be deemed as evolutionary change and therefore consistent with hypotheses of natural selection, it would need to show that variation that corresponds to differences in mortality and or reproduction. So most of this research that we are discussing is showing correlations that exist, but is not showing that these correlations have any correspondence to differences in mortality or differences in reproduction. So in summary, anthropometric measurements show both genetic and environmental influences. Human growth and development, as one example, portrays patterns throughout human populations that can be affected by many different things, including climate, nutrition, disease, and even differences between sexes, between males and females. However, keep in mind that not all of these factors have been shown to be the direct result of natural selection, just as I said on the previous slide. Just because correlation is being shown, that does not mean causation. Therefore, it doesn't mean that the correlation is a result of natural selection occurring in the population.